And hello back. Hello, welcome back, not hello back. Hello, welcome back to our radiation heat transfer learning journal. On the last video, we were talking about going on to blackbody radiation, right? So yeah, blackbody radiation and spectral emissive power, and we were talking about some of that. Now I just want to make a correction about last video. Okay, so I did say something about spectral emissive power. Spectral emissive power. It's something like energy emitted. Energy emitted per unit what? Per unit area. Okay, so these are the things we consider: the area, per unit time, per unit frequency, and what else? Let's check back. So energy per emitted energy per unit time per surface area per frequency, right? So energy per time is power, and this is the area, and this is the frequency, right? All right. So spectral emissive power is as such, and I also mentioned in the last video that let's say if you have a bigger area here, if the receiving area, let's call this the receiving area, AR. If the receiving area is bigger, the energy transferred from, let's say, this area dA to this area AR will be bigger. Of course, that's true. However, the spectral emissive power, when we talk about per unit area, we are not referring to this. We're actually referring to this area. So there was a mistake in the last video. I just want you to be clear about it. What area we are talking about when you're talking about spectral emissive power or total emissive power for that matter. So you can see a total emissive power, you just integrate this across with the frequency. So I'm just going to copy this up and put it here. And as you can see, okay, this is kind of redundant. Okay, this as well. Okay, so this is a spectral emissive power, just so you are clear. So it's energy per unit area, per unit time, per unit frequency. All right, so this is the area. This is the area we're talking about. Now I want to move on to, okay, what is the spectral emissive power of a blackbody spectrum? So spectral emissive power of a blackbody spectrum. So there are lots of ways to derive this, okay? Lots of ways to derive this, okay? But I'll give you the long and short of it, right? Basically, through some quantum physics and derivations, the spectral emissive power of a blackbody is given by this formula over here. Okay, so let's take a look at, let's talk about blackbody. Did I already put, yeah, blackbody emissions, yeah. Let's talk about blackbody, yeah. So let's take a look at each of the terms of this formula. So EBV stands for blackbody, and is based on the frequency. So you can see it's mainly based on two parameters here. One is the temperature. So obviously with higher temperature, a black body will emit more radiation. And just for a reminder, black body is something that absorbs all the radiation incident on it, and emits emits radiation according to this temperature. Okay, so it is the best absorber and the best emitter. Okay, so okay, 2 pi. Don't know why that is there. And then you have H. H is the Planck's constant. All right. H is the Planck's constant. So this is actually derived from quantum physics. So quantum physics, if you're not sure what it is, it just means that, let's say you have an atom, you have electrons, and those electrons are at certain energy levels. That's most of what quantum physics is about when we talk about energy. We have discrete energy levels that are allowed and disallowed at the quantum states. Okay, so give you an atom energy level diagram. So alright, so you have this, for example, your electron is here, and it can be promoted by some sort of light with energy HV. It will be promoted to here, and then when it releases, when the electron drops back down to this energy level, it will release this photon of light with the same energy, E equals HV or E equals HF. So it's not just the electron shells that have specific energy levels. Sometimes the atom itself or molecule itself has a specific energy level. For example, let's say you have a molecule of carbon dioxide. Let's say you have a molecule of carbon dioxide. It should be flat, sorry. Alright, it's a molecule of carbon dioxide, and it can vibrate in certain ways. So again, there are only a fixed number of ways that this thing can vibrate, right? So if it's at the ground state, then it will probably have a certain level of energy, and if it's at the excited state, then it will be vibrating some certain way. So there are certain fixed bands. This is what quantum physics is about. And this is the most relevant part of the quantum physics. It's basically that there are discrete energy levels at the subatomic level or at the quantum level at a very small scale, and atoms and molecules can only attain certain fixed energy levels, and they can transit through those. This is the most important part of quantum physics, so don't be afraid when you hear this quantum physics. Alright, okay, anyway, we use I think I said V just now. We should call it nu. That's the correct Greek letter. Okay, the derivation I have kind of typed it out later. So nu to the power of 3 and n squared, n being the refractive index. Okay, so next thing is c0 squared. C0 is the speed of light in a vacuum. That's why there's a naught over there. Then you have exponential h nu divided by kt. So this is some sort of an Arrhenius relationship. So if you have ever seen an Arrhenius relationship before, you'll see what do you call that? Let's say there's a rate constant. It's some exponential into some activation energy, or some energy over RT. So this is Arrhenius relationship. So you can see something pretty similar to the Arrhenius relationship here. It says that it compares the energy level of the photon to, let's say the characteristic energy or temperature, average energy or temperature, whichever that is. All right. So this is the Blackbody emission spectrum, given by this formula here. Okay. So the spectral Blackbody emissive spectrum. So remember, it's just based on quantum physics. Alright, it's based on quantum physics. So what was the quantum physics just now? I have already explained to you. So atoms and molecules can only take on certain discrete energy levels, and that's how the formula was derived. So I'm not going to derive the formula from scratch here. It's going to take too much time and frankly not very relevant to us, as engineers. So this is the Blackbody spectrum we've copied just now. So what are some of the properties of Blackbody radiation? Okay, right, I've written Planck's law here. And what is Planck's law? Planck's law is basically the formula you have been seeing here. So it is called Planck's law. All right. Okay. So let's take a look. I've written some stuff here. Basically, I've just rewritten the formula here. Okay. I should cover the rest of this up. Okay. Never mind. Excuse me. So what am I writing here? I'm just rewriting the formula that I have stated above. Okay, so just nice you see this C0 square and N square here. If you combine these two terms together, you can actually have this Cn squared. There should be a square there. Cn squared. So this is the speed of light in the said medium with a refractive index of n. Okay, so what are some of the properties of Blackbody radiation? Blackbody emits radiation in all directions equally. All right. So it doesn't, this thing is direction independent, right? So I'm gonna take this part out. Okay, maybe I'll just put this in here. I'll put it in the document, the Word document which I'm talking about, and I'll just cut this out. Now I'll just paste it over here. So this is the quantum physics I'm talking about. Okay. Alright, so yeah, it emits radiation in all directions equally, which is kind of convenient for us. Alright, because not all bodies do that, but a black body does that. So it will emit in all directions equally. Okay, all directions equally, so not a problem. How much energy is being emitted? It's based on this. And if you want to find the total energy emitted, you just simply do the same thing we've been doing above. If you have energy emitted, spectral emissive power, which is energy per unit time per unit surface area per unit frequency, we can do the same. We can do the same for you can just integrate over all frequencies, and you just find the energy per unit time per unit area. So this is the, what is it called? Total emissive power. So you can see the total emissive power. You just do an integration here. So that's the concept, right? And sometimes, you know, people don't just express the blackbody blackbody spectral emissive power using frequency or nu. Sometimes people like to use wavelength or wave number. And if you just copy these parts here, you can see that the using the wave relationship, the C equals to F lambda, okay, or C equals to N F lambda, or C equals to N nu lambda. Can you see here? Let me zoom in. Okay, never mind, can't zoom in. Okay, I've copied and pasted here, so it's bigger. So C equals to nu times N times lambda. So speed of light in a vacuum equals to the refractive index times the wavelength times the frequency. Okay, so and we know wave number eta here, which you can see here, this is just 1 over the wavelength. Okay, now if we wanted to express, let's say, this black body emissive power in terms of wave number or wavelength, we do have to do some change of variables here. So you can see what they're doing here is to express dV, or no, d nu in terms of lambda, as you can see over here. So that's you do some differentiation on this, and then you arrive at this long little thing here. Similarly, if we want to change it into in terms of eta, we just do again a differentiate nu with respect to this d eta. Then you'll get this relationship here. Okay, so and what is this equation saying here? Alright, so the total emissive power for black body, it's the integral of the spectral emissive power for black body over all frequencies, or if you're writing in terms of the wavelength, it is integrated across all wavelength, or in terms of wave number, which is eta. You just integrate the expression according to these formulas here, the wave number. Okay. Now, one thing to take note of, because nu and lambda are kind of in opposites, I mean, they are inversely proportional to one another. So if you kind of differentiate one, you get the negative of the other. You see here? Because this is a 1 over lambda, you tend to have a negative sign pop out during your differentiation, because you are differentiating 1 over lambda. When you do that, you take the negative 1 times 1 over lambda squared. So that is the result of that. So that's why there's this negative sign here. You just got to be pretty careful about it. Okay, so this is what we have again. Now what I'm doing here, okay, is slowly to show and prove to you what these what these expressions actually look like. Okay, so we have this, we start out with this according to the frequency, right? Okay, but let's say we want to do it in terms of say wavelength, right? So the wavelength, okay, we use this relation EB Blackbody equals to, alright, let me just do it to make it clear, integral from 0 to infinity, okay, E B nu d nu. Alright, so this is what we get here. Okay, now however, we also say the same thing here. If we want to do it in terms of wavelength, that's what we need to do. 0 to infinity EB lambda LAMBDA d lambda. Alright, so what we are doing at the bottom is to equate integral of the blackbody spectral blackbody emission, emissive power, and express it in terms of the wavelength, because both of these are equal. If we want to change to the wavelength, we want to see what this EB lambda is, right? Because this expression will differ from this expression. So how do we derive what is this EB lambda? Well, the process is simple. We just equate both of these integrals. So the top is this integral you see here. Alright. So if you want to get the d lambda, replace this dv, d nu with d lambda. So what is d lambda? You see this complicated expression here for d lambda. So d nu equals to minus c naught n lambda squared, and you multiply this whole thing here because we differentiate. So what I've done is just to copy this expression here after we have differentiated it, copy it and paste it over here. So all I've done is to take this expression, which is this, and replace d nu with whatever you see here, because as we were talking about earlier, d nu equals to this expression. Alright, of course you kind of have to change the variables here from 0 to infinity as well, but yeah, so that there'll be kind of a negative thing. So here it should be 0, because infinite frequency means the wavelength is 0. Zero frequency means infinite wavelength. So this is how it corresponds. So what we have to do is, if we want to switch the limits around, we got to take the negative sign out and do it as such. So what we are left with is this expression. Okay, so we are integrating from 0 to infinity EB lambda d lambda. So where's d lambda? D lambda is here, and this whole lot in here, if we just compare, okay, if we just compare as such, like so, integrate from 0 to infinity, d lambda is outside here, d lambda is outside here. So what we conclude is that EB lambda is whatever this expression is on the inside. So this is what I've written here. Okay, so but you can see it's still in terms of frequency, so we can just do a simple change of equation to substitute all of this in here. Therefore, EB lambda is this expression you see highlighted in yellow here. Alright. So how do we get expression for that? It is based on this. Okay, spectral emissive power for blackbody. And yeah, again, if we want to do the same, for the one in terms of wave number, all we have to do is just repeat, wash, rinse, and repeat this same procedure. So what we start with is this black body. Just ignore whatever's at the bottom first over here. Pay attention here. So okay. So we again equate the total emissive power for black body of the frequency to the wave number. In terms of frequency, the one in terms of frequency to the one in terms of wave number. Okay, so to find the expression for this, we'll need to just do the same replacement of variables. So again, we'll have something like this. So we'll replace this equation, this EB new here. Alright, this EB new here with this whatever messy expression this is. And then we'll need to find an expression for d new. And as we see, d new equals to C naught over n, 1 minus eta over n, dn d eta, and d eta. So again, that's done by differentiating both sides of this. It's pretty straightforward. So what we can find is that d new equals to C naught 1 minus eta over n, dn d eta. So what we do is we have this long expression here inside, which is equals to this expression we see here. So this expression is equals to this expression. So if you want to compare, EB eta equals to this whole thing on the inside. And how do we get rid of the frequency? We can just use this equation here, substitute inside to this frequency new, and then we get the expression we want over here. This very messy, very messy expression. So wherever new pops up, we just replace it by this, similar to how we do it here. And the final result is this. We have 2 pi h blah blah blah, and okay, so I'm not going to simplify this. This is the final equation we have. I'm just going to leave it as it is. Okay, so this is how we actually find black body spectral emissive power in terms of wavelength and in terms of wave number, if we have something, the frequency to start out with. Okay, yeah, so this is pretty much what Planck's law is about. Yeah, in the next video, we're probably going to talk a little bit more about other aspects of Planck's law. For example, how do we integrate this whole thing in future videos anyway. May not be the next one, but in future videos, we want to see how to integrate this whole thing to get a black body emissive power, to see what this EBT is actually like. And of course, we'll also explore other things as well. So thanks for watching. I'll see you guys in the next video. Bye bye.